VSEPR Chem. This is Unit 2 review. I'm recording this a week in advance, I estimate. This is recorded on September 13th, 2025. You can fact check me on that. So anyway, this is going to be your Unit 2 review. Alright? So, let's get started. I have the College Board website pulled up on my phone, and so I know what I'm talking about. So the first topic you cover in Unit 2 is types of chemical bonds. Now there are three types here that you learn about. Ionic, covalent, and metallic. Alright. So ionic bonds, they're sort of like the Coulombic attraction between positive and negative ions. So what does that mean exactly? So if you have a negative ion, we'll say that this is chlorine, or chloride rather, and if you have a positive ion, say that this is sodium, Na. These two attract each other by Coulomb's law, which bonds them together to form sodium chloride, NaCl, or table salt. And this works for any pair of ions. Lithium and fluorine, they form ionic bonds as well. Aluminum and fluorine, they form ionic bonds as well. This also works with polyatomic ions. So if you have a sulfate, for example, and a calcium, right? These two bond, they have Coulombic attraction, and so they get calcium sulfate. Right? So this works with any sort of ion. So quick recap of ionic bonds. It is a Coulombic attraction between ions. Alright? So this is what an ionic bond is. Now you might be wondering, how do I determine whether a molecule is ionic, covalent, or metallic? We're getting there, okay? Now covalent bonds, these are usually between two non-metals. Ionic bonds are between a metal and non-metal. I probably should have mentioned that, I'm sorry. Now M in this case represents metal, and M represents non-metal. So covalent bonds usually form between nonmetals and nonmetals. So Nm and M. Alright? And so this is sharing electrons between two atoms. Alright? So if you take the example of fluorine, that is two fluorine atoms bonded together. If you remember, fluorine atoms have 7 electrons each, and they each want 8. Right? And so what this can do is sort of like put the 2 electrons in the middle so that they share, okay? Now these 2 harpoon arrows represent 1 electron being moved, and so they're moved to the middle. And so this forms a covalent bond between fluorines, like so. Notice how I'm drawing all the electrons so that I can count up my electrons later. Now, fluorine has 7 valence electrons here, and so I have 7 electrons on the valence electrons in this fluorine and 7 valence electrons in this fluorine as well. The left and the right fluorine. And so what happens is you have 1, 2, 3, 4, 5, 6, 7, 8. Yes, I know. 6, 7, whatever. 7, 8. And 1, 2, 3, 4, 5, 6, which 8 plus 6 is 14. And this bond here is considered to be part of both. And so the left fluorine has 8 electrons, and the right fluorine also has 8 electrons. Therefore, they both satisfy the octet rule, and they're both happy. Now, I just showed you an example of 2 halogens bonding together, F2, alright? But what about something a little bit more complicated? Maybe like carbon dioxide, CO2, right? Now notice how C has 4 valence electrons and O has 6. Give me a moment. Alright? And so what this can do is it can go here, here. The oxygen can put the radicals here. And it can do the same thing on the other side with the other oxygen. Now this forms carbon dioxide, which has a double bond to both the oxygens. And this is what it looks like. Notice how C doesn't have any electrons around it because all of its electrons were used within bonding. Okay? Do you get that? Okay. Now, there's one more type of covalent bond before we can get to polarity, alright? And that is the triple bond. Triple bonds are kind of rare, but let me show you an example. You have 2 nitrogen atoms, okay? Each of them has 5 electrons, like so. Alright. Now, notice how these have 3 radicals, okay? And so I'm going to start drawing the harpoon arrows over here, and maybe you can kind of see what I'm doing here, which is this. This triple bar represents a triple bond. It is extremely hard to break, and nitrogen is actually one of the strongest bonds on Earth. It is extremely strong, and that is actually why you need to convert it into ammonia in order to use it as fertilizer. Okay? Good. So, now you might be wondering, okay, what about polarity? We're getting there. Now, as a quick review of our covalent, it is sharing electrons between 2 nonmetals. And this E- represents an electron. Non-metallic, as you can guess, is between 2 metals. And what sort of happens here is kind of weird. Okay, so if you remember, metals have sort of like a transition metals, especially, sort of have a weird electron configuration. So bear with me here. Okay, what the metal can do is it can shed some of its outermost electrons and become a positive ion. Now this isn't an ionic bond. Okay, what this is a delocalized system of electrons. Now, delocalized just means that the electrons aren't bound to any nucleus. They're free to move around. And this is why metals are such good conductors, actually. Okay? So all these dots that I'm drawing here, these represent all the electrons, and they can move any way they want. Okay? Now, this is a delocalized system of electrons. If I had drawn them in circular orbits, that would have been a localized system of electrons, and that would have represented something like a covalent bond. Okay? And this model is actually sometimes called the sea of electrons model. Okay? Now, if I'm going a little fast for your taste, you can always slow down the video or pause it. So the sea of electrons model is literally describing what's happening. You have cations, and you have a sea of electrons around the cations. Okay? So, what now? This is actually where the electronegativity periodic table comes in. You might have noticed it when you first came into the video. Okay? So, if we have an electronegativity difference, delta En, of 0.5 or less, right? This is what's called a nonpolar covalent bond. Alright? And this means that the electrons are shared roughly equally among them. if we have an electronegativity difference delta En that is greater than 0.5, we'll put it here, but less than 2 or 1.9, this is called a polar covalent bond. Now the electrons here are more skewed between one and another. Okay, so as an example, water, right? H2O. This has an electronegativity difference, if you look up here, 3.5 minus 2.1. This is an electronegativity difference of 1.4. Okay? And so the hydrogens actually become partially positive, and the oxygens actually become partially negative, and this is what is called polarity. There is another requirement for polarity that I will get into later. Okay, so keep that in the back of your mind. Now, if the delta En is greater than 2.0, this is considered ionic bonding. And so, if you take lithium and fluorine, that has a delta En of 3, which would be considered ionic. Aluminum and chlorine, it's a little bit different. Aluminum has an electronegativity value of 1.5. Chlorine has 3.0. So aluminum and chlorine would be technically polar covalent bonding, but what we notice is that they exhibit what is called bridge bonding. Now that is very complicated to get into, and so we don't need to worry about that for now. Okay? So now you have types of chemical bonds now, and you have what makes them different. All right. I'm gonna erase the entire scene now, and let's get into intramolecular forces, which are just bonds. Okay. So what intramolecular forces are, right? I just explained it. They're bonds. However, they can vary in strength. So if you have an HH bond, right? Now I'm drawing this very specifically, right? Let's say that this is the ideal length, okay? And it has the least amount of potential energy. Remember that you want the least amount of energy possible, okay? So delta E must be at a minimum to be considered ideal. Alright? So as an example, right? Let's draw a little graph here, okay? So what will happen? So let's graph energy on the y-axis and distance on the x-axis. Alright, so now let's say that this is right over here, HH. Alright, this is where the energy is at its minimum. Now what happens, right? What do you think will happen as you push the atoms together? What do you think will happen? You will probably answer the energy will exponentially increase as the nuclei are repelled. Now, if you don't know that, that's okay, because since we're pushing the nuclei together, the nuclei are repelling since they have the same charge. And remember, this is Coulombic repulsion. Coulombic attraction is between two different charges. Coulombic repulsion is between two of the same charges. Okay, and so as we go to zero distance, we actually cross the x-axis, and this is what it does. Now, if we pull it away, it's a little bit different, right? Because this is an ideal length. If we pull it away, then our squared factor in Coulomb's law becomes bigger and bigger and bigger. And if you remember, this is inversely proportional. Okay, this is inversely proportional to the radius, and so as the radius gets bigger, the attraction gets smaller. And so what will happen is it approaches the x-axis and it doesn't actually cross it, sort of like an asymptote, okay? And so what you'll probably see on the AP exam is something that looks a little bit like this, with two hydrogen atoms that are basically not attracted to each other anymore, and two hydrogen atoms that are way too close to each other, okay? They're almost fused, okay? So this is what intermolecular forces and potential energy are, okay? So you have way too close up here, you have ideal distance down here, and you have way too far right here, okay? And so if you have either of the two edge cases, you will either pull back apart in the way too close case, or pull back together into way too far case, to lower potential energy, and to the ideal bond length. Alright? And so now, let's go ahead and talk about structure of ionic bonds. Now remember, ionic bonds are usually between a metal and a non-metal. Okay? So ionic bonds are usually between a metal and a non-metal. And this actually has some pretty neat consequences in relation to structure. Like how, in the case of, say, something like sodium chloride, right? You have plus, minus, plus, minus, plus, minus, plus, minus, and it goes on and on and on, right? Now, this alternating pattern continues below it. So you have minus, plus, minus, plus, minus, plus, okay? Now, I'm obviously not going to draw the entire grid over here, but you can probably extrapolate what will happen. This is plus, this is minus, this is plus, this is minus, this is plus, this is minus, this is plus. Alright? And so this is the structure of this type of ionic bond. This is one that is one positive ion with one negative ion. So if you have, say, like 2 MgSO4, right? You mainly probably won't see this in the AP exam, but the Mg2 plus, right? And it's going to be surrounded by 2 minus, magnesium chloride, sorry. This is going to be surrounded by minus and minus. And so this will continue on, alright? And so that sort of checkerboard pattern happens again and again. Alright? What you'll mainly see is one positive ion with one negative ion in this unit. Okay? So you don't exactly need to know that edge case, but it's good to know just in case. Okay? And so now we go to metallic bond, which is alloys. Okay? So alloys and metals, right? We already discussed the metallic bonding, right? In which positive ions are trapped in a sea of electrons, right? The positive ions are rigid and the electrons are free to move wherever. Okay? What an alloy can do, right? What an alloy can do is it can sort of sneak into that lattice, alright? So let's say this is our metal, right? For the sake of example, we'll say that we are trying to make steel and this is iron, okay? Now, all these circles represent iron atoms, okay? Now, these red circles, these red smaller circles represent carbon atoms, okay? And so this is what is called, is what an alloy is. It's the doping of one substance with another substance. Now, I can't remember what this one is called. It's not an interstitial alloy, it's the other kind of alloy. Now, what an interstitial alloy is, if I can, this is going to be in black, okay? If you remember, stitch, that's kind of how I remembered it, right? stitching, you're sort of like doing two things of the same size, right? If you are stitching. So if we have something like this, right? Then an interstitial alloy can plug up all of these holes and sort of like have the same size as the other metal atom. Okay? So if we were to make stainless steel, this is how it will be made. Okay? So these are metals and these are alloys. Okay? Metals have a sea of electrons. Alloys have multiple metals and or non-metals in that alloy, in that sea. Okay? So now we get to the culmination of this unit, right? Which are Lewis diagrams, Lewis structures. So what a Lewis structure basically is you have a central atom, we'll say A, right? And you have some amount of terminal atoms, right? We'll say X, right? Now, this is what a single bond looks like, double bond, and triple bond, okay? So, if you have, say, hydrogen fluoride, right? Remember that each atom wants to have an octet, or in hydrogen's case, a duet. That is a very important exception to note. Okay, and so this creates hydrogen fluoride. This is an example of a single bond. I accidentally violated the octet rule for fluoride there, but it's okay because I have an eraser, sort of thing. Now, I already showed you examples of double bonds and triple bonds, and so let's get this show on the road, shall we? Now, Lewis diagrams can actually be a very cool example of another thing, right? And that is VSEPR, or VSEPR, if you want to be extra fancy, right? And this stands for valence shell electron pair repulsion theory. And what this basically says is atoms are basically clouds of electrons, and they will space out as much as possible from the other atoms, such that the valence shell electron pairs will ideally have a mostly uniform spread across the central atom. And so if we have, and I'm gonna use AX here, right? So if we have AX2, the atoms spread out. The atoms spread out, and they can't get any farther than a 180-degree angle, and so that creates a line, and this shape is known as linear. Alright, so I'm going to put shape up here, angle up here, and the formula up here, right? Now AX3, and actually, before I get ahead of myself, A represents the central atom, X represents the terminal, or the edge, right? And E represents an electron pair, a lone pair. Sometimes you can have radicals in these shapes. For the most part, you won't have to worry about these. And so for AX3, these atoms can't go farther apart than a triangle shape, where each terminal atom represents a vertex of the triangle. So if you have the atom at the center of the triangle, if you imagine like this is what it looks like, right? And so this, as you can guess, is what's called trigonal planar. Triangle planar, because it's in a plane. Alright? And this has an angle of 120 degrees. And so, what you can have is AX2E. Right? And this is a shape known as bent. Now, remember that electron pairs actually repel a little bit more than just regular bonds or atoms, right? And so this actually has an angle slightly less than 120 degrees at about 119 degrees, alright? And so these are all the possible combinations for AX2 and AX3. Now if you get to AX4, the atoms can now rearrange into 3D space. and so the furthest they can possibly be is on the vertices of a tetrahedron, and so it shouldn't be a surprise. This is known as a tetrahedral shape. I misspelled tetrahedral. And so this has an angle of about 109.5 degrees between each atom. Now, what you can have is AX3E, completely different from AX3 that we mentioned here, okay? AX3E has one lone pair, which, remember, repels slightly more, and so this is known as trigonal pyramidal, because it forms like a sort of little pyramid, which is 107 degrees. And then you can get to AX2E2, which is known as bent yet again. However, this is a different kind of bent than the AX2E mentioned with the trigonal planar. This bent is about 104.5 degrees, which is actually the shape that water exhibits, and is why it's such a good absorber and a solvent, right? And so now this is everything that you can have with AX4. Now AX5, this is where it gets a little bit interesting. Now, what some people will actually do is they will list it as AX3Y2. Now, this is actually referring to two positions on this type. The X's here represent the equatorial positions, right? The little plane that is formed by the X atoms. And the Y2 represents the axial positions because they align on an axis. And so this is called trigonal bipyramidal. Now, why is it called this? Well, let's derive the word. Trigonal, meaning triangle, bi, meaning two, and pyramidal, meaning, well, pyramid. And so what it's saying is that the central atom is the center of a trigonal bipyramid, and that all the atoms are the vertices of said trigonal bipyramid. And so this actually has two angles. It's a little bit of a consequence, okay? And so for the XX angle, this is 120 degrees, sort of like a trigonal planar. For the XY angle, right, this is 90 degrees because it is between a plane and an axis that is perpendicular to the plane. And for the YY angle, since it's on an axis, it is 180 degrees. Okay? And so now, we get into a little bit more tricky stuff. I'm going to switch back to the AX notation now. So AX4E, if you remember, E represents a lone pair, and so this actually creates a shape known as seesaw. Now, why is it called seesaw? Now, that is because, if you look here, this is what AX5 looks like. This is what AX4E looks like. Right? Now, if you turn it on its side, it kind of looks like a seesaw. Right? You can sort of imagine that two kids are sitting up here, right? And they're doing like their little thing on a seesaw, right? And so this is why it's called a seesaw shape, right? And so the XX actually becomes slightly lower at like 119 degrees. XY keeps its angle at 90, and the YY obviously keeps its angle of 180. Okay? You got that? Now, if we go AX3E2, this is what's known as T-shaped. Right. Yes. Alright, so the reason why this happens, excuse me, dang it. So the reason why this happens is because AX2E2 looks a little bit something like this, where the lone pairs actually take the equatorial positions now, and it actually did before. And so what this is a 90-degree angle, and this is a 90-degree angle, right? And so if you look at it from the plane that the 4 atoms are in, it kind of looks like a T, which is why it's called T-shaped. And so the angle here is 90 degrees all around. And of course you have AX2E3. This is exhibited by certain ions, and the lone pairs have completely taken over the equatorial position, and what you're left now is with the axial positions, which forms a line with the center atom, which is why it's called linear. And the bond angle here is 180 degrees. And now we have one more sort of family, alright? This is called AX6. And what it is octahedral. Octohedral. If you can imagine an octahedron, what it's saying is that the center atom is the center of the octahedron, and all the terminal atoms represents the vertices. Okay, and so this has 90 degrees all around. Now AX5E1. This has a configuration known as square pyramidal. I'm just going to label it PYR for now. And this still has 90 degrees all around, because if you imagine you're substituting one of the axial positions for a lone pair, this forms a square pyramid where the octahedral once stood. And so now if you remove another axial position and add another lone pair, what you now get is square planar. 90 degrees all around once again, and this is actually because of, yet again, you have a square plane and 2 electron pairs coming out of the plane. These are where the one's axial positions stood. Okay? AX3E3 is once again T-shaped, 90 degrees all around, and AX2E4, which is also derived from this, is linear. You got all that? You can slow it down, but you need to memorize all of this, okay? I went a little fast, but you can always slow down if you need to, okay? I don't want you to fail your exam. I simply want to get through this before 7:30 my time, because I'm hosting an event at 7:30. And so we've just covered Lewis diagrams and VSEPR. Now all that's left is resonance, formal charge, I'll label FC, and hybridization. And this is kind of like all the same thing. So resonance, if you remember, right? Not all the bonds in some atoms are created equally, right? So if you have the nitrate ion, right, NO3 minus, you might remember that it looks a little bit something like this. But why does the double bond have to be on this oxygen? Why can't it be here or here? Well, it actually can be on all 3, right? And so what this looks like is like it's like sharing the electron between all 3, right? And so this is what's called resonance. And resonance basically just means that you don't have to pick which one actually is the correct one. You can just smush them all together and find the commonalities. Like how this has at least one single bond, right? And this is where it gets kind of confusing. The double bond here is on all 3 of the oxygens. But you're asking, but how can that be? Well, here's the thing. The double bond is spread across all 3 of the oxygens, and so all 3 of the oxygens sort of have that double bond character. And this actually creates some weird effects, like how the nitrate ion has, even though it has two single bonds and one double bond in the Lewis structure, it actually only has one bond length. And that is because of this resonance hybrid, is what it's called. Now, this is exhibited with a lot of different ions, not just nitrates, and in fact, it can be exhibited in a lot of different molecules as well. You can exhibit it in carbonates, and a lot of other atoms. I can't think of them off the top of my head. But this is basically just another delocalized system. This is the delocalized system. Now, if you remember, delocalized means that the electrons can move wherever they want within the molecule, of course. And so what formal charges are, right? Let's go back to our example of nitrate. I'm not actually gonna do the resonance hybrid for anything else, but it's good to know, right? So what you can actually do for formal charges is you can actually draw like a little circle around the atom and count up the electrons listed, right? And nitrogen has its own circle as well. So normally oxygen has 6 valence electrons, nitrogen has 5. And, alright, and so, oxygen here, right, notice how this part of the bond is here, and so this counts as 1 electron, as the other electron is with nitrogen, alright? So if you count 1, 2, 3, 4, 5, 6, 7, now this actually gives oxygen a -1 formal charge, right there, right? And this also applies to this oxygen. If you count the double bond on oxygen, 1, 2, 3, 4, 5, 6. Alright, so this is neutral. 0 charge. And if we count up the nitrogen, 1, 2, 3, 4. This has a +1 formal charge. And so overall, the entire molecule has a -1 charge. Alright? So what you can do for formal charges is you can literally just draw a circle around the atom and count up the electrons in the circle. Now, if you end up drawing to include a bond, then that bond only counts as 1. Okay? Okay. Now, if I'm going a little fast for your liking, remember, you can always pause the video, slow it down. Alright? Let's go back to hybridization. So hybridization is a little bit of a consequence of a theory known as valence bond theory. Basically, the only things that can bond are valence electrons. So what will happen is that if you have N, right? Let's go back to nitrate, right? Usually what you will do, right, is since this is a double bond, the oxygen has this is known as a pi bond, and this is a sigma bond. Yes, I know, sigma. A pi bond is formed from the side-by-side overlap of p orbitals. If you don't know what p orbitals, check out Unit 1 slides, or check out Unit 1 on College Board. They have very good notes there. Sigma bonds are from head-on overlap between s orbitals, p orbitals, like so, and this new type of orbital called a hybrid orbital. Now, notice how I'm drawing a hybrid orbital, right? This is important to how it works later. So what a hybrid orbital is basically you're taking an s orbital and a certain amount of p orbitals, right, to form a new type of orbital called, if you have 3, right, you have sp3, 1s, p3, 3 p's, right? So this is what an sp3, sp2, and sp, right? And these leave different amounts of p orbitals unreacted so that they can form pi bonds. And depending on how many p orbitals you leave, you can have different amounts of pi bonds, right? So if you have the example of nitrogen, right? This has 2 pi bonds and 1 sigma bond. And so the sigma bond is caused by the overlap of an sp orbital. And since the pi bonds are formed from the overlap of two p orbitals, there must be 4 p orbitals left over altogether. And so if you have a triple bond or 2 double bonds, that atom is usually sp hybridized. If you have 1 double bond, that atom is usually sp2 hybridized, and if you have no double bonds, the atom is usually sp3 hybridized. I hope that you will find this video helpful, and as always, ace your test.